Today we're going to be doing 10.3b, determining convergence or divergence of other sequences. In order to do this, we're going to have to take the limit of the sequence. So basically, as n is getting larger, we're going to be seeing if the terms get closer to L. L is just some number. If they do approach some number, then the sequence is convergent because the limit exists. And if they do not approach some number, that means the limit does not exist, which means that the sequence is divergent. So for example 1, we're going to consider the infinite sequence right here. Notice right here, a sub 1, it has a value of 1, a sub 2 has a value of 1/2, and so on, which means the formula for this sequence can be written as a sub n equals 1 over n. Notice that as n is increasing here, the terms are approaching a value of 0. So what I mean by that is this. This is 0.5 if you look at 1/2. This is 0.3 repeating for 1/3. This is 0.25 for 1/4. And this is 0.20 for 1/5. This pattern is continuing. So what you'll notice is that these numbers are getting smaller and smaller. Since this is an infinite sequence, this is going to keep on going to infinity, which means that our numbers are going to be getting closer and closer to 0. So we can say that as n increases, the terms are approaching a value of 0. Since it approaches a value of 0, we're going to say that this limit is convergent. Here is how we can say all that in a summarized notation. This is read as the limit of 1 over n as n approaches infinity equals 0. Once again, because this equals 0, which is a number, this sequence is convergent. Moving on. We can actually take this and generalize it to any fraction where the n is in the denominator and its exponent has a positive value. That's what this means right here. R is greater than 0. So when you have any positive power of n and it's in the denominator of the fraction, as n is getting larger and larger, the limit is going to equal 0 no matter what. There's one other one that's not on this paper that I want us to talk about real quick. So I'm just going to add it in right here. And that is the limit as n approaches infinity of n to the r. This is saying as n is getting larger and larger, what are the term values approaching? So if you wanted to kind of plug some stuff in just to see, you could. But what we're going to find is this is just going to keep getting bigger and bigger without bound. So in this situation, the limit does not exist. For example, if you want to add a little mini example right here for this one, if I gave you the limit as n approaches infinity of n squared, what would that equal? Well, think about it. The first term has a value of 1 squared, which is 1. The second term has a value of 2 squared, which is 4. The third term has a value of 3 squared, which is 9. Let's jump up ahead a little bit, and what would the 10th term be? It would be 10 squared, which is 100. So these numbers are getting larger and larger without bound. As n gets larger and larger, or is approaching infinity, the sequence is also going to approach infinity, and therefore the limit would not exist. Remember, infinity is not a number, it's a concept. So here are some of the limit laws that we looked at in an earlier chapter. So you can see if you're adding two limits, then you can split them up and take the limit of each one individually. This one right here says that if you have a limit of a constant times a sequence, you can pull the constant out. This one is a good one. The limit of a constant is the constant. And you can kind of see through the rest of these. Okay, this one says determine whether the sequence converges or diverges. If it converges, find the limit. So what we're going to need to do, our very first step in all of these problems to determine whether or not converges or diverges, is we must take the limit. So your very first step for all of these is the limit as n approaches infinity of your sequence. And in this case, this is our sequence right here. So after we've done our first step of taking the limit, what we're going to do next is split this into two fractions by using this heart method or pretzel method, however you know it. So we're just going to, again, need to write the limit because that's the essence of this. The way that we can determine whether or not it converges or diverges is by the limit, so that needs to be on every step. So we have 1 over n squared plus 3n squared over n squared. After you do this, now you can see that we can reduce right here. So next step is to reduce. These are going to cancel right here. Okay, what we're going to do next now is we're going to use some of our limit laws to break this up so we can evaluate it. So the limit as n approaches infinity of 1 over n squared plus the limit as n approaches infinity of 3. So we're down to this line right here, and what we can realize right here is we have 1 over n to some power. So again, as n is getting larger, this whole fraction is getting smaller, and in fact it's getting closer and closer to 0. So the limit of this fraction right here is 0. And if you look back at your limit laws, it says the limit of a constant is the constant. So we have a limit right here of 3. 3 is a constant number, so it's 3. Notice how once I've evaluated the limits, I no longer need the limit sign there. So our limit is going to equal 3. Because we have a number, because this has a limit, the series converges. Okay, so when you start the problem, because we're determining convergence or divergence, you have to take the limit. So here I've written the limit as n approaches infinity of 5n squared plus n minus 4 all over n squared plus 1. Because there's two terms down here in the denominator, we're going to use a different approach than we did in part A. So again, the reason why I'm going to use this new approach is because I have two terms down here and not just one. So notice right here we've given you this little hint. Divide the entire expression by the highest power in the denominator. The highest power in the denominator is n squared, so we're going to take each term in this fraction and divide it by the highest power in the denominator. So you can see this can take a lot of steps, and some of you are going to be able to do this in your head. I'm really just trying to spell it out here for you so that you can get it from home. If you have any questions, you can always ask. So here's what we have when we divide everything by the highest power in n. This preserves our equality since we're dividing everything by the highest power of n. So what you're going to want to do now is reduce all those fractions. So we get 5 plus 1 over n minus 4 over n squared all over 1 plus 1 over n squared. So you're starting to see some of those terms, the 1 over n. We'll talk about what to do with this right here since there's a 4 right now. So what we're going to do is we're going to split these up into the individual limits using our limit laws. So this one, and yes, you do have to do this. Every single one of them needs a limit. You have to do this so that you can evaluate it according to your definitions. Now this one right here, what we're going to do is we're going to pull that constant out in front of the limit. And then we still have to divide these all by the limit as n approaches infinity of 1 plus the limit as n approaches infinity of 1 over n squared. So once we have all this, you can see we have all our limits. So now I'm going to evaluate these. So the limit of a constant is the constant, so that's 5. This right here is 1 over n, so that's going to be going to 0. That was one of our definitions. We have this 4 in front here, so we can bring that out in front of the limit. The limit of 1 over n squared is also 0, so we have over 0. And then down here, we have the limit of a constant is the constant. And then here, we have that 1 over n to some power, which is 0. So from that point, we can just do our math. 5 plus 0 minus 4 times 0 is going to all be 5. 1 plus 0 is 1. 5 divided by 1 is 5. So because this has a limit, it has a number of 5, this sequence will converge. Okay, so now let's take a look at C. Again, we always start these problems by taking the limit as n approaches infinity of the sequence. This is again based upon the definition. Okay, how many terms are in the denominator? There's only one term in the denominator. Because there's only one term in the denominator, we're going to do the same thing we did in part A, which is split this fraction into 3 fractions. So again, you have to have the limit along every step of the way. So we have that right there. So our next step is going to be to simplify. And at this point, if you're getting good at this and you want to split up your limits at the same time as you simplify, that would be fine with me. So that's what I'm going to do right here. The ends are going to cancel here. And then on this last one right here, I have a 2n, and so because I have that 2n there, a more proper way to write this would be to put that 2 in the front since it's a constant. So now we're going to evaluate this. So let's start with this one. This is that same sequence we keep seeing over and over again. Because it's 1 divided by n, this is going to approach 0. And then this one right here, because we have the limit as n approaches infinity of a constant, our limit is the constant, so 5/2. And then we get to this one right here. This one right here, think about what's happening. As n is getting bigger, what's happening to the sequence? It's also getting larger. Because this sequence is also getting larger, it's increasing without bound, and therefore the limit does not exist. So this one, even though there's a 2 in front, is still going to be does not exist. So if any part of your sequence, the limit does not exist, the entire sequence does not exist, and therefore it's divergent. Here's our last example on the front side of this page. It has the sequence equals the sine of n. And for this one, we are going to start off by taking the limit as n approaches infinity of the sine of n. What we're going to do here is, instead of trying to figure this out algebraically, we're going to actually just draw a little graph right here. So you're going to have to remember your sine graph. So remember, sine starts at 0, 0, and then there's those 5 points. And it has a height of 1 and -1 for the minimum. And this graph keeps on going to infinity. What we want to know is, as n is getting larger, what is happening to the graph? So even if we were to keep on continuing this, since it's a periodic function, the graph would look like that. And we can see that the sine graph is oscillating between -1 and +1. Because it's oscillating between +1 and -1 and +1 and -1, it's not converging, which means that this graph is divergent. Okay, so continuing on here with problem E, our first step again to determine convergence is to take the limit of the sequence as n approaches infinity. So we're going to take a more intuitive approach here, and we're going to look at what is happening as n is getting larger. So you can see that that's what this notation means right here. As n is getting bigger and bigger, what's happening to our sequence? Well, since n is an exponent in the denominator, what's happening as this denominator is getting bigger, the whole fraction is actually getting smaller. So just like our sequence that's 1 over n, this one will also converge to 0. So we're going to write, just as notes for ourselves, as n gets larger, the denominator gets larger. Making the fraction get smaller. With all that said, we can say that the limit as n approaches infinity of 1 over 5 to the n is going to get closer and closer to 0, so it's going to converge to 0. Since the limit exists, this sequence converges. So now we're on to f, and what we're going to do is we're going to actually break the sequence up a little bit to be able to evaluate the limit. So we have a sub n equals -1 to the n times n over 8n plus 1. The reason that I'm going to do this is because this piece right here of this sequence is really, its job is to alternate the terms from negative to positive. So for example, if n was 1, -1 to the first power would make this a negative term, and if n was 2, -1 squared would make that positive 1, so the next term or the second term would be positive. So what we're going to do is we're going to temporarily ignore this right here because all it's doing is switching from negatives to positives, and we're just going to take a look at this piece right here and see what's happening for that part of the sequence. So we have this right here because we have two terms in the denominator. We're going to be using the method we did in problem B, so we're going to be dividing by the highest power of n. Notice that there's a coefficient in front of the n. It's okay. We're still just going to divide by the highest power of n. We do not have to divide by that coefficient too. So the limit is n approaches infinity of n over n all over 8n over n plus 1 over n. And then again, we have to split this up. So if you would like to split it up as you're simplifying, that's fine. The limit as n approaches of infinity of 1 all over the limit as n approaches infinity of 8 plus the limit as n approaches infinity of 1 over n. So now that we have these broken up into their limits, we can use our limit properties. So the limit of a constant is the constant. This limit is also the limit of a constant, so it's going to be that constant of 8. And then we see that 1 over n sequence that we've seen in many of the other problems, and we see as n is getting larger, the denominator is also getting larger, making this whole fraction smaller, which is making it approach 0. So if we're just looking at this piece of the sequence, what's happening is the sequence is converging to 1/8. However, because we still have this -1 to the n, what's really happening is that when n is an even number, -1 to the n equals 1. And when n is odd, -1 to the n is equal to -1. So as n is getting larger, the sequence that we have, which is -1 to the n times n over 8n plus 1, is oscillating. So it oscillates between -1/8 and 1/8. Thus, the limit as n approaches infinity of this sequence does not exist. So therefore, those are therefore symbol in math, the triangle with 3 dots, the sequence diverges. So we really spelled that out right there just to make sure that we understand what's going on. So again, this term right here is making it oscillate from negative to positive, which means that this whole sequence is going from -1/8 to +1/8, and so therefore, because it's not approaching a single value, it's oscillating between two, it's going to diverge. So So now we're going to get to the last problem of this type, and you can see that -1 to the n again, and students make the false assumption that whenever you see -1 to the n, that a sequence is going to be oscillating. So we include this example here so you can see that that's not always the case, so don't make that assumption. So how do we start all of these problems? Again, because there's a -1 and we know its role, we're actually going to take it out of the limit just temporarily. So we have this right here, and now we're going to take the limit, because whenever you want to determine whether or not a sequence converges or diverges, you have to take the limit. And I'm just going to reduce this right away, so n squared over n cubed will reduce to 1 over n, and we know that this limit is equal to 0. So the interesting thing about this one that differs from the previous problem is that even though -1 is going to alternate between -1 and +1, when I do -1 times 0, I still get 0, and when I get -1 to an even power, which would make this +1 times 0, I'm still going to get 0. So the limit as n approaches infinity of our sequence equals 0. Because this is a number, we know that the limit exists, so it converges. What we need to do is write the formula for the sequences, or the formula for the nth term. They all mean the same thing for these sequences right here. So what I always want my students to do is I want you to go ahead and find the pattern. So in this case, I'm adding 2 each time. And we've already discussed that when you add 2 each time, that would mean there's a common difference. So our formula is going to start with 2n, and then what we want to do is check it using the first and second term. So a sub 1 is equal to 2 times 1, which is 2, and that's my first term, so that works for that one. You always want to check it. You can do this mentally for more than one term just to make sure. So this works for the first and the second term, so we're good. So now we're going to move on to part B, and what I always tell my students to do is always make whole numbers fractions, because usually it's easier to see the pattern. So what we're going to do here is we're going to notice that, hey, this has the same pattern as the previous one does, but in the numerator. So since I'm going to have a numerator and a denominator, I'm going to put a fraction bar. So I have 2n, but what I notice right away is that when I plug in 1, 2 times 1 is 2, and I need the first term to be 3. So a fast way to get that, and the way to get that, would be to put a +1 there. So now I'm going to check it for another term. So this is the fourth term right here. 2 times 4 is 8 plus 1 is 9. So I'm getting the numerator of the fourth term, so that's good. And then down in the denominator, I'm going up by 1 each time. Because I'm adding 1, it means it's arithmetic. So I'm just going to put an n there. And you can see that this, no matter what term number you plug in, will give you this sequence right here. For example, if I plug in 5, 2 times 5 is 10, plus 1 is 11, divided by 5. So that's the fifth term right there. So that one's good. So let's go ahead and move on to this next one. So I'm going to put +2, +2, +2, +2, same pattern again. So I know it's going to be a sub n equals 2n. Again, my starting term, if this was the sequence, would be 2, because 2 times 1 is 2, but it's 7. So how am I going to get from 2 to 7? I would need to add 5. So I'm just going to check for the fourth term this time. What's 2 times 4? That's 8 plus 5 is 13, so this sequence is good. So let's go ahead and try part D. Again, making that fraction, So let's go ahead and try the next one. Again, making any whole numbers fractions so that I can making the whole numbers fractions so that I can see the patterns easier. I'm going to notice here that I'm adding 1 each time, so it's still arithmetic. So a sub n equals 1n, or just n. And then on the bottom, I am adding 2 each time. So again, still arithmetic, so 2n. But since it's 2n, The first term for 2n would give me 2 in the denominator, but since it's 1, I'm going to subtract 1. And this time I think I'll check it for my third term. So when I plug in 3, I get 3 in the numerator. And when I plug in 3 to the denominator, 2 times 3 is 6, minus 1 is 5. So that gives me that right there. So now we're going to move on to part E. Notice that this term is going back and forth between negative, positive, and we learned earlier in the lesson to get that, all we have to do is put this right here, negative 1 to the n. So when you plug in 1 for the first term, it'll be negative 1. When you plug in 2 for the second term, whatever our pattern will be, this negative 1 will be squared, which will make it positive. So now what I'm going to do is I'm going to look at this and I'm just going to see adding numbers doesn't really change things, but what I am noticing is that these numbers are perfect squares. So if these are all perfect squares and what is changing is the number inside my parentheses, I'm going to make that my variable and then put a square there. Okay, so I'm going to use the fifth term to check it this time. Negative 1 to the fifth power is negative 1, and 5 squared is 25. Negative 1 times 25 is negative 25, so that one works out there. Moving on to F, you got to take a look at your powers here. This one is now going up by multiplying of 4. Change that to a dot. Multiplying of 4, multiplying of 4, multiplying of 4. So what this is going to do is if you're multiplying by 4, it's going to be something like this right here. So I get powers of 4. So this would be my common ratio. This numerator is geometric, and n is how it's changing. So 4 to the first power, 4 to the second power, and so on. In the denominator, I notice that I'm going up by 3's, and it's multiples of 3 instead of adding 3. So I have this ratio right here. The other way that you could write this, because they're both to the power of n, is 4/3 to the n. And you could check any of them. Let's check the third one just to make sure. 4 to the third power is 64, and 3 to the third power is 27, which would give us 64 over 27, so that one works. Okay, so for letter G right here, we are going to first notice that we're just multiplying by 1 each time. So in the numerator, we will have a 1. And then in the denominator, we're going to notice this pattern. So first of all, I'm going to make my whole number a fraction, just hopefully so I can see it easier. And what I notice is that from this one to this one, I multiply by 2. And then from this one to this one, multiply by 3. This one to this one, multiply by 4. This one to this one, multiply by 5. And so the way that we come up with patterns where it's 2 times 3 times 4 times 5 is by using the factorial notations. So I get n factorial, and then I'm just going to make sure that this works out. So I'll try it with the fourth term. So 1 over 4 factorial, which equals 1 over 4 times 3 times 2 times 1, which is 1 over 24. So that one does work out. Moving on to letter H, we see we have 1/3, 1/2, 3/4, 9/8, 27 over 16. It looks like these right here are getting multiplied by 3, but this one doesn't quite look like it's fitting the pattern here. Down on the bottom, it looks like these ones are being multiplied by 2, and again, that first term isn't quite fitting the pattern that we see right now. But what we're going to do is we're going to use these later terms to try and establish a pattern. So because we're multiplying by 3, this would be 3 to the n. So notice if I plug in 1, 3 to the first power is 3. And that's actually my third term, not my first term. So how many terms away am I? I'm 2. So I'm going to subtract 2 to see if that gets me what I need. So again, plug in 1. 1 minus 2 is -1. 3 to the -1 is actually 1/3. So that seems like it might be right. In the denominator, I'm going to do 2. And my first term, if I just have 2 to the n, would be 2, and I actually need it to be over here, so let me see what happens when I subtract 1. Now watch what happens here. what is 2 to the 1 minus 1? It would be 0, so 2 to the 0 would actually be 1. So what we actually have is this situation right here, where the first term for the numerator would be 1/3, and the first term for the denominator would be 1, but that just reduces to 1/3, which is why I say to look at your later patterns. Our very last problem where we have to write the sequence is right here. So we're going to just take a look at our pattern, and again, like I've said all along, anytime you have a single number, you're going to want to write it as a fraction, because then you can start to see the pattern that's happening there. So in this one right here, you can see that we have a 5 along the way, so we're going to keep that 5 just as a 5. It's not changing. And then you can see that these terms are all cubed, and what's changing is the base. So we're going to make the base the variable, and then we're going to put a cubed on it. And then down here you have 1, 2, 3, 4, 5, so that is just n. And if you check your terms like we've been doing all along, let's take the third one. 5 minus 3 to the third power divided by 3 would give us the third term right there. So we're good.